All right, so let's say given this diagram here where we have this rotation about the xy axis, and the question says, what is the angular acceleration for this circular motion? To start, we know that for a rotating body, theta represents the displacement. So given this rotating body here, this rotating body travels around the circle, starting at theta 1 equal to 0, and it travels through an angle theta to a position theta equals 2, and this distance here is going to be delta theta, where delta theta is the change in angular position, and it can be quantified as equal to theta 2 minus theta 1. You know, in general, velocity is the change in position over change in time. So for circular motion, the angular velocity is equal to change in theta over change in time. Theta and x are both displacements, and then v and omega are both velocity values, where omega is the angular velocity of an object pointing along the rotational axis. So if we have our diagram here with our changing angle, by the right-hand rule, omega is going to be pointing out of the page, because if we curl our right fingers in the direction of motion, our thumb's going to point out of the page. So in the x, y, z coordinates, this also means that w is going to be pointing in the z direction, because if we draw our motion in the xy plane and curl our fingers, we can see that our thumb points up, and that's in the z direction in this case. So both these diagrams here express the same thing. But what is the angular acceleration? We can extend normal acceleration to circular motion. So we know that acceleration is equal to the change in velocity over change in time. And we know velocity is equal to change in position over change in time. So acceleration is equal to the second derivative with respect to position over change in time. So if we extend it to circular motion, a is actually going to be equal to this alpha, and x is the same as theta. We saw that earlier. So if we just plug that in, we can see that the acceleration is the second derivative of the change in theta, or the change in omega being the velocity vector over change in time. So visually, this means if acceleration points in the angular velocity direction, this means that the angular velocity is increasing, which also means that the rotational motion of the object is increasing. And this is analogous to the normal xva relationship, just for normal motion. When velocity increases, the acceleration increases, because the acceleration is equal to change velocity over change in time, and it's also equal to v2 minus v1 over t2 minus t1. So when velocity increases, the velocity at point 2 is going to be faster than velocity at point 1, which means v2 minus v1 is positive, so that means the acceleration is positive. So this same relationship is seen with our circular coordinates theta, omega, and alpha. If our angular velocity increases, this also means that our angular acceleration increases.